Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Qari bin Warusli, and I'm going to share about the chapter 1 for the introduction, background, objective, and scope for this lab. Um, for the introduction of the determination of the friction loss in pipes is fluid flow in a pipe follow a certain governing equation. One of them will be continuity equation. The mass of the fluid going into the pipe will equal the mass of fluid going out of the pipe. Viscous fluid and Newtonian fluid, a fluid which does not flow easily. Viscosity come into effect, causing laminar or turbulent flow. Viscosity also causes fluid friction in the effect of the reduction of total energy in the fluid flow. For the background study of the lab is water, like any viscous fluid flowing through a pipe experiences a loss in pressure due to friction. Can express this pressure loss in terms of the loss of heat, where it is vertical drop through which the fluid flow, heat flow, heat loss consists of major and minor losses. And this equation heat loss equals to major plus heat loss of minor. Um, and this is for the major losses. The Darcy Weisbach equation can be used to predict friction loss in a circular pipe. We use this equation, which is F times LV square over 2dg, where HF is loss of head due to friction, L equals to length of pipe, D is diameter of pipe, P is mean velocity of flow in the pipe, and F is the Darcy-Weisbach friction factor. And for the minor losses, we use this equation K times V square over 2G. Which is K is dimensionless loss confidence obtained the experimentally. And for the objective is to design and evaluate complete measurement technique and experimental procedure for fluid flow and determine major and minor losses in the different piping system, and to investigate the velocity for the different diameter of pipe. And for the scopes is to determine whether a laminar or turbulent flow will occur during the experiment, and to find out how different pipe size affect velocity. The range of flow rate will be connected to the friction factor. And that's all from me. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Nurul Razia, metric number MA18092. I will be covering the theory part of the friction losses in pipe experiment. The pressure drops and head loss during flow through pipes and ducts are directly connected to the friction in pipes. Only a few examples, such as fully developed laminar flow in a circular pipe, have theoretical solution. The geometry, surface roughness, flow velocity, surface temperature, and fluid type all influence the transition from laminar to turbulent flow. The Reynolds number, which is the ratio of inertial forces to viscous forces in a fluid, determines the flow regime. The Reynolds number can be determined using this following formula, where the V average is average flow velocity, D is the diameter of pipe, V is the kinematic viscosity of the fluid. Viscosity effects in straight pipes cause the majority of piping system losses. Frictional head losses are significant in a lengthy pipe and must not be overlooked. The viscosity of the fluid, in this case water, the internal pipe diameter, the internal roughness of the inner surface of the pipe, the change in elevation between the pipe's end, and the pipe length all influence overall head loss. Pressure losses are often described in terms of the equivalent fluid column height, called the head loss, HL, and defined as equation below in pipe system analysis, where HF is the loss of head due to friction, L is length of pipe, D is diameter of pipe, V is the mean velocity of flow in pipe, and F is the Darcy-Weisbach friction factor. The additional height that the fluid must be lifted by a pump to overcome frictional losses in the pipe is referred to as head loss. The previous equation is valid for both laminar and turbulent flow, where for laminar flow it is Fd equal to 64 over Reynolds number, and for turbulence flow it's Fd equal 0.316 divided by Reynolds number to the power of 0.25. These losses, which are called minor losses in a system with long pipes, are minimal in comparison to the total head loss in the pipes, and are caused by viscous effects in pipe components such as fittings, valve, and bending. Minor losses may be bigger than major losses in some instances. Minor losses are usually expressed in terms of the loss coefficient KL, as this equation, where HL is the pipe system head loss and defined as the difference of P divided by the density times gravity. The loss coefficient of a component can also be calculated by measuring the pressure loss across the component and dividing it by the dynamic pressure KL, where the inlet and outlet diameters are equivalent. Once the loss coefficient for a component is available, the head loss for the component is determined from this equation. The loss coefficient is determined by the component geometry as well as the Reynolds number. It is, however, widely thought to be independent of Reynolds number. The flow has substantial Reynolds number and the loss coefficient in most situations. In terms of equivalent length, the minor losses can be defined as this equation, where F denotes the friction factor and D denotes the diameter of the pipe in which the component is contained. As a result, the head loss can be calculated by multiplying the entire pipe length by the length equivalent. Once the loss coefficient is available, the total head loss in a piping system can be determined by this equation. As you can see in this equation, the total head loss is composed of major and minor losses. That's all from me. Thank you.
Assalamualaikum and hello. My name is Nur Halimah binti Manap. My metric number is MA18077. Today I will explain about method and procedure. Experiment apparatus. Number 1 show fluid friction apparatus. 2 is hydraulic bench. 3 is pressure sensor. 4 is data measurement and data acquisition. Procedure. First is all of the equipment is checked to see if there are any damage. Second is the DAQ and NI are connected to the pressure sensor. 3 is the straight pipe, which is the required tested pipe, is adjusted to two pressure sensor input and output. Next is the main switch are the pump and the pump are both turned on. The flow rate of water is regulated by spinning the control knob, starting at the highest flow rate and steadily decreasing the flow rate of water. 6 is the flow rate is the measure using a flow meter or a computer. 7 is all the pressure valve and the pressure value from both sensors are read by the computer. 8 is for elbow pipe, bend pipe, 45-degree bend pipe, and 90-degree bend pipe. Repeat step 2 until 6. 9 is all the data collected are tabulated. Precaution. First is when taking readings, the parallax error should be avoided. Second is when fluid is flowing, the manometer reading may fluctuate, notes the means position carefully. Lastly is carefully maintain a fluid level in the input and outlet supply tank. That's all for me. Thank you.
Assalamualaikum and good day to Dr. Moin. My name is Muhammad Wa'id Daimi from section 1 group D. Today I'm going to talk about the result and discussion about the experiment done on lab 3. So there are two experiments done for this lab. First, which is major loss in state pipe. Here we can see that the result for the experiment 1, the volumetric flow both in meter cube per second and liter per minute. The measure head loss, the flow speed, the Reynolds number, coefficient of friction, and calculated head loss. Then here we can see that the head loss versus flow speed, in which the graph shows that it is rising. And then moving on to experiment 2, minor loss. In minor loss, we have the data for volatile flow in both meter cube per second, liter per minute, and we have the flow speed, the measure head loss, calculated friction coefficient, Reynolds number, loss coefficient, calculated head loss, and equivalent length. So here we can see that the result for the head loss versus flow speed. The 45-degree pipe show the highest head loss compared to band pipe and elbow pipe. Then here we can see that the head loss versus equivalent length for elbow pipe 90 degree, for the band pipe 90 degree, and for 45-degree pipe. All of them show the same trend, which is rising. Which is rising as the head loss was with the equivalent length. Then moving on to the discussion in the experiment. What is the dependence of head loss upon velocity in the laminar turbulent flow region of flow? In laminar flow, the head loss is proportional to velocity rather than velocity squared. In turbulent flow, head loss is directly proportional to the square of velocity. What natural forces affect the pipe roughness? The pipe roughness is affected by corrosion, because corrosion causes the surface roughness inside the pipe to change, which change the flow rate capacity and cause high pressure drop. What is the significance of change in temperature to the head loss? The significance of change in temperature to the head loss is that as the temperature rise, the viscosity and density of the fluid will rise. Due to this, head loss will be different. So explain how the strain gauge sense the pressure. The strain gauge sensor is touched or compressed when pressure is applied. The system will vary dependent on the degree of deflection generated by pressure in the axis parallel to metal flow design with the current flow rate. This term refers to the conversion of external force into an electric signal. So what are the two types of energy loss that is usually associated with pipe flow? Major loss linked with friction energy loss owing to medium viscosity effect and pipe wall roughness, and minor loss due to pipe heating, change in flow direction, and flow are two common forms of energy loss in pipe flow. Based on the testing result, modern head loss modelled by pipe heating are the most significant. So what happens to the head loss if the diameter of the pipe is decreased and the length of the pipe is decreased? So in order to find about this, we use the formula HL, head loss equal to F per LD V square over 2G, in which F is the drastic friction factor, length of the L is equal to length of the pipe, V is equal to mean flow velocity, D equal to hydraulic diameter of the pipe, and G is the gravitational acceleration. So based on the formula, head loss is linearity related to pipe length, but inversely to pipe diameter. As a result, as the pipe length decrease, the head loss decrease, and as the width of the pipe decrease, the head loss increase. So that's all for me. Thank you.
Okay, so my name is Hana Huaida binti Nusra Effendi with a metric ID MA18161. Okay, so for chapter 5, conclusion. So for the conclusion, students can use the friction loss in a pipe apparatus to investigate the transition from a laminar to turbulent flow and determine the critical Reynolds number. The setup represents the transition from laminar to turbulent flow and is suitable for both demonstration and student experiment. So the experiment values for major and minor heat loss are calculated and compared to theoretical values throughout this experiment. So the frictional force in the straight pipe caused significant heat loss, whereas the loss coefficient of the various pipe fittings causes small heat loss. So it may be stated, so for experiment 1, from experiment 1, when the fluid means velocity increases, so the head loss also increases. Meanwhile, for the experiment 2, it can be stated that as the fluid mean velocity increases, the head loss also increases. So some elements such as instrument factors, human factors, and environmental factors can and will influence to the inconsistency of the results that we get from this experiment. So that's all from us. Thank you.